Okay, in this video, we're going to talk about section 1.7 dealing with linear inequalities and absolute value inequalities. And in this video, we're going to talk about how to use interval notation. We'll find the find the intersections and unions of intervals. We'll solve linear equations, recognize inequalities with no solution or all real numbers as solutions. And then we'll solve compound inequalities and solve absolute value inequalities. Okay. So the first thing we'll talk about in this section would be interval notation. Now, some sets of real numbers can be expressed using interval notation. Suppose that A and B are two real numbers such that A is less than B. Okay, so we'll start with the open interval. Now, the open interval has parentheses like this around the A and the B. That represents the set of all real numbers between but not including A and B. So in this case here, the open interval AB, if we write that in set builder notation, it will be this: the set of all x such that x is greater than A and less than B. The set of all x such that x is greater than A and less than B. That's considered to be the open interval. And the graph looks like this. Here we got parentheses at A and B to indicate that those endpoints are not included. And we shade in between to indicate that all the values of x are in between A and B. But here the endpoints are not included. And also we have the closed interval. Now the closed interval has brackets. And those brackets indicate that your endpoints are included. So here, the closed interval, A comma B, represents the set of real numbers between and including A and B. So here, if we write that in set builder notation, it will be this. It will be the set of all x such that x is greater than or equal to A and less than or equal to B. Okay. That's how we would formally read that set builder notation. Okay. The graph looks like this, where you see brackets at A and B, and we have the interval shaded in between to indicate that the values of x are between A and B, and we do include A and B. All right, next we have the infinite interval. Infinite interval. Now, in this case here, we use this symbol, infinity. And the infinity symbol looks like the number 8 lying on its side. Okay, that's infinity. So the infinite interval, A to infinity, and here they're using the parentheses, that represents the set of real numbers that are greater than A. Okay, so here this means in set builder notation that we have the set of all x such that x is greater than A. And this is what the graph looks like. We put the left parentheses at A, we shade to the right of A to indicate all the values of x greater than A. Also, the other infinite interval is negative infinity. And in this case, they're using a bracket at B. So this would represent the set of real numbers that are less than or equal to B. Okay. So here, this is the negative infinity symbol that tells us that it extends indefinitely to the left, where the positive infinity symbol says that it extends indefinitely to the right. Okay. But for this right here, negative infinity to B, this means in set builder notation, the set of all x such that x is less than or equal to B. And here's the graph for that. A bracket is placed at B, a right bracket is at B, and we shade to the left indefinitely. Okay. Now, when to use parentheses and brackets in interval notation? We use parentheses to indicate endpoints that are not included in the interval. So in other words, if you have less than or greater than, we use the parentheses. Square brackets indicate endpoints that are included in the interval. So for less than or equal to, or greater than or equal to, we use brackets. That's probably the best way to put it, okay? So anytime you have less than or greater than, we just use the parentheses, or less than or equal to or greater than or equal to, we use brackets. Okay. Now on the next page is pretty much the interval notation. Here I've listed all the interval notations that you're probably going to be seeing in this section and their appropriate set builder notation and what the graph looks like. Okay. Now I'm trying to clear this up so that way this first one shows parentheses. The second one is brackets. This next one will have a bracket on the left and a right parentheses. The other one has a left parentheses and a right bracket. These two are what we call half open or half closed intervals. And then the rest of these have infinity in it. And keep in mind, infinity, whether it's positive or negative, always uses parentheses because it goes on and on and on forever without end. This one has a bracket, parentheses, parentheses, and a bracket. And this one, parentheses. That last one, negative infinity to infinity, that's the entire number line. And the set builder notation would be the set of all x such that x is a real number, or sometimes they use this symbol, the capital letter R, for the set of all real numbers. Okay. Now, we're going to use these 9 interval notations to answer these questions here at the bottom of this handout. Like this one right here. Excuse me. Here we're going to express each interval in set builder notation and graph. So here we got -2 and 5. Now notice it looks like this. So we got to pick which one of them, which one of these looks like example 1A. And by looking at it, I do have a left bracket and a right parentheses right here. That's going to be this interval notation. So this is what the set builder notation would look like. The set of all x such that x is greater than or equal to A and less than B. Okay. So here's the set builder notation for that. The set of all x such that, -2 has the bracket, so it's going to be less than or equal to. X will be in the middle, but the 5 has the right parentheses, so it's just strictly less than 5. So that is the set builder notation for this. Okay. And then next they want us to do the graph of that interval notation. Okay. So I'm going to draw a number line. I'm going to put 0 here. I know -2 is to the left of 0 and 5 is to the right of 0. So in this case here, -2 is included because of the less than or equal to, and because of the bracket that you see there. I will put a left bracket at -2. 5 is not included, so I'm going to use a right parentheses at 5. And to indicate that all of my x values are in between -2 and 5, I'm going to shade in between. Okay. All right, now the next example is 1 and 3.5. And notice that it has brackets there. One comma 3.5 has brackets on both of them, so it's going to be the second one. And it's going to be this set builder notation right here, where you got both less than or equal to symbols there. So in set builder notation, the interval 1 and 3.5 is this, the set of all x, such that the 1 has the bracket, so it'd be less than or equal to x, and less than or equal to, since the 3.5 has the bracket. So it's a set of all x such that x is greater than or equal to 1 and less than or equal to 3.5. And also we need to do the graph as indicated in the directions. So I'm going to put 0 in the center. Let's see, 1, 2, 3, and 4. Now 3.5 is halfway between 3 and 4. So that point there will be 3.5. All right. Now the 1 and the 3.5 both have brackets. So I'm going to put a bracket at 1, a left bracket at 1, and a right bracket at 3.5. And to indicate that the value of x is between 1 and 3.5, we'll shade in between those two, like this. Okay. And finally, part C, -infinity to 1. All right. So we're going to find which one of these matches this right here. So -infinity, and we got a right parentheses there. So it's got to be this one right here. And this is your set builder notation, the set of all x such that x is less than b. So in this case, -infinity to 1 is, in set builder notation, the set of all x such that x is less than 1. Okay, that's the set builder notation. Now we need to do the graph. It's 0. 1 will be to the right of that. Now 1 is not included as indicated with the right parentheses. So I need to put a right parentheses at 1. -infinity is indefinitely to the left. So that means we need to shade to the left of 1. And also, if you looked at your subbuilder notation, you can see that less than symbol points to the left. That tells you you need to shade to the left of 1. Okay. All right, next we'll talk about intersections and unions of intervals. Intersections and unions of intervals. Okay, this symbol right here, A with the upside down U and B, that means A intersection B, or the intersection of A and B. That's going to be the set of elements common to both sets A and set B. And the other one is the union. Looks like the U right here. So A with the U and then B, that's going to be A union B, or the union of A and B. That's going to be the set of elements in sets A or set B or in both sets. And here we're using the inclusive or, because it could be in set A or in set B or both A and B. Let me give you an illustration of that. Let's say I had two sets here, like set A had these elements 3, 4, 5, 6, and 7. Set B had these elements 4, 6, 8. Okay. Now, if I wanted to find the intersection of A and B, I want to find out what elements are in both A and B. And if you look at it, 4 is in A and B, and also 6 is in A and B. So the intersection of A and B would be the elements 4, 6. And then for A union B, the union of the two, we're putting the two together because we're combining the elements that are in A or in B or in both A and B. So here we just write each element only once. So this will be like 3, 4, 5, 6, 7, and 8. So we're just combining the two together, listing each element only once when we do the union of A and B. Now we're going to be using this idea when we deal with intervals here. So when we find the intersection and the union of intervals, we're going to do this. We're going to graph each interval on a number line. That's step number 1. And then number 2, you're going to find the intersection by taking the portion of the number line that the two graphs have in common. In other words, you want to find out for the intersection where these two graphs overlap, where the overlap happens. And if you're finding the union, you're going to take the portion of the number line representing the total collection of numbers in the two graphs. In other words, you're going to take the furthest endpoint on the left and the furthest endpoint on the right of those two. That's how you're going to find the union of those two intervals. Okay. So now in this case, let's say we wanted to find the intersection of the open interval 1, 4 and the closed interval 2, 8. Now notice that they graphed the open interval 1, 4 on the number line like this. And they graphed the interval, the closed interval 2, 8, as you can see, like this. Okay. And now what we need to do here is find out where the overlap occurs. Okay. And if you look at this, you'll see that the overlap occurs from 2 to 4. That's where the overlap occurs. Now the question is, are we going to use the bracket or parentheses? Here's a hint. If that endpoint is included in both of the intervals, then you use the bracket. If the endpoint only occurs in one of them, is included in only one of them, you need to use parentheses. Take a look at the 2. The 2 is in both of these because here we have a bracket at 2 and 2 is included in that first interval. So we use the bracket for the 2. But for the 4, we have a right parentheses here, and 4 is included in the other. But here, it's only included in one of these, mainly the second one. So we have to use parentheses. So this is the notation for your intersection. 2, 4, where 4 is not included. That's the half open or half closed interval. Okay, now let's say we want to find the union of these two. So we're going to use these same 2 intervals here, but this time we're going to find the union. Now, as you notice, for the open interval 1, 4 is graphed, and for the closed interval 2, 8 is also graphed on here as well. Now, to find the union, we use the furthest endpoint on the left and the furthest endpoint on the right of those 2 graphs. If you compare the left side, the furthest one on the left is the 1, and it has a left parentheses there, so we use a left parentheses at 1. The furthest endpoint on the right of these 2, as you can see, is 8. It has a bracket, so we use the bracket at 8 and shade in between. That represents the total collection of those 2. So the union of the open interval 1, 4 and the closed interval 2, 8 is this. 1, 8, where 1 is not included in that interval. Okay, let's look at a couple of examples of this. Let's say we want to use graphs to find each set. In this case here, we got the closed interval 1, 3, and the intersection of the closed interval 1, 3 and the open interval 2, 6. So we want to find the interval that represents the intersection. All right, so first of all, we need to, I'm going to do 3 number lines here. So we're doing 3 number lines here. That first number line would be for the closed interval 1, 3. I'll start right here with 0, and then 1, 2, 3, 4, 5, and 6. Now notice that we have brackets at 1, brackets at 1 and at 3. So we need a bracket on the 1 on the number line and a bracket at 3 on that number line as well. And we shade in between to indicate the values of x are in between 1 and 3. The second number line will be for the open interval 2, 6. Let's see, this will be 0, 1, 2, 3, 4, 5, and 6. At 2 and 6, we have parentheses. So we'll use a left parentheses at 2, because that's an open interval, and a right parentheses at 6. And we shade in between to indicate that the values of x are in between 2 and 6. Okay. So that's my open interval 2, 6 on the graph. And now, on that third line, we want the intersection of the 2 intervals. All right, in this case, anytime we're finding the intersection, we have to find the overlap of those 2 intervals. Where do these 2 graphs overlap? And if you look at it, from 2 up to 3, that's where the overlap occurs. So now I need to find out which do I need to use, parentheses or brackets for each endpoint. Take a look here. For the 2, 2 is included here in the first interval, but it's not included in the second. It has to be included in both for me to use the bracket. In this case, it's only the 2 is only included in only one of those intervals. So I have to use the left parentheses at 2. Now for the 3, it's included in both. Because at 3, I have a right bracket. 3 is included in the second. So we use a bracket for that at 3. And we shade in between. So that is what the graph of the intersection of those two intervals are. So this means the intersection of the closed interval 1, 3 and the open interval 2, 6 will be this 2, 3, and 3 has the bracket for that. All right, now for part B, we got the union of these same two intervals here. The union of the closed interval 1, 3 and the open interval 2, 6. Well, I've already got those graphs there. I can use that to come up with my graph for the union of the two. So this means when I'm finding the union of the two, I need to take the furthest endpoint on the left and the furthest endpoint on the right of those two intervals. Okay, so now I'm going to cover this up. Taking a look at these two, the furthest endpoint on the left would be right here at 1. And it has a left bracket at 1. So that means I'm going to put a bracket at 1. And then if we look here, the furthest endpoint of these two on the right would be right here at 6. And at 6, I have a right parentheses. So I put a right parentheses at 6 and shade in between. All right, so that means the union of these two is going to be this interval from 1 all the way up to 6. 1 has the bracket and 6 has the parentheses. Okay. All right, next we're going to talk about how to solve a linear inequality in one variable. Now we did talk about linear equations earlier in the first chapter. Now we're going to look at inequalities. Okay, and you should be familiar with inequalities because they have one of these 4 symbols, either less than, greater than, less than or equal to, greater than or equal to. And also, I should say 5, because it's also not equal to, but we're not going to use not equal to. We're just going to focus on the first 4, less than, greater than, less than or equal to, or greater than or equal to. Okay. Solving an inequality is a process of finding the set of numbers or solutions that make the inequality a true statement. The set of all solutions is called the solution set of the inequality. So in other words, with equations, you are only finding at least one solution. But in this case, with inequalities, you're trying to find all solutions that will satisfy that inequality. Set building notation and interval notation are used to represent solution sets. Now, there's one thing you need to know when we solve linear inequalities. You'll do the same thing as you would if you were solving linear equations. However, there's this one rule. When we multiply or divide both sides of an inequality by a negative number, I'm going to underline this word negative, because this is important. When you multiply or divide both sides of an inequality by a negative number, the direction of the inequality symbol is reversed. That means you're going to switch your inequality symbol to the opposite direction. Okay, and these are the three properties of inequality. One is the addition property of inequality, meaning if you take the same quantity and add or subtract it from both sides of that inequality, then the resulting inequality is equivalent to the original one. So in other words, your inequality symbol will stay the same. The same holds true for the positive multiplication property of inequality. Multiply or divide both sides of an inequality by a positive quantity, your inequality symbol remains the same. But for the negative multiplication property of inequality, if you multiply or divide both sides of an inequality by a negative number, that means you reverse your inequality symbol. Like in this right here, when you got negative 4x is less than 20, you divide both sides by negative 4, but you're going to reverse that inequality symbol from less than to greater than to get x is greater than negative 5. And we're going to look at a few examples of that right now. So in this case here, we're going to solve and graph the solution set on a number line. That's going to be very important. Solve and graph the solution set on a number line. Like in this one, 2 minus 3x is less than or equal to 5. Two minus 3x is less than or equal to 5. In this case here, we need to get x by itself. So first, let's get rid of the 2 that's in front. That's like a plus 2. So that means we need to subtract 2 on both sides. So that's gone. You're left with a negative 3x. You have the negative sign in front. Negative 3x is less than 5 minus 2, which is 3. And to get x by itself, we're multiplying by negative 3. So that means we need to divide both sides by negative 3. But in this case, we're dividing both sides by negative in an inequality. So that means this less than or equal to changes to greater than or equal to. And then 3 divided by negative 3 is negative 1. So here we got x is greater than negative 1. And now we need to graph the solution set on a number line. All right, number 1 is to the left. Now, notice the inequality symbol of greater than or equal to. That means that negative 1 is included. So that means we're going to put a bracket at negative 1. And of course, greater than points to the right of negative, well, to the right. So that means we're going to shade to the right of negative 1, like this. So that's what the graph of that solution set is. Now, I think in the homework, they may want you to give either your answer in set builder notation or interval notation. Well, let me give you the interval notation, and then I'll give you the set builder notation. In interval notation, it's going to be this. From left to right, the bracket is at negative 1. So we got negative 1 with a bracket. This goes on indefinitely to the right, so that means infinity. So that's the interval notation. Now for the set builder notation, That's going to be this, the set of all x. That bar means such that, and then we copy down that inequality symbol. I mean, inequality statement that we got when we solved it. X is greater than or equal to -1. Okay. All right, here's another example. Solve and graph the solution set on the number line. Let's say we got variables on both sides of this inequality. 3x plus 1 is greater than 7x minus 15. All right, so now we're going to solve this inequality for x. Now, when we do this, it would be best to put the variable on the left-hand side of the inequality. So that means I'm going to move the 7x over to where the 3x is. And I'm going to do that by subtracting 7x on both sides. So now I got 3x minus 7x. That's -4x plus 1 is greater than, bring down that -15. And I should say bring down the negative in front of the 15 because I see people forget to bring that down. So now to get -4x by itself, we're going to subtract 1 on both sides. That's because we're adding 1. So -4x is greater than -16. Now, when I divide both sides of this inequality by -4, this inequality symbol of greater than changes to less than. Then -16 divided by 4 is 4. So the solution set would be x is less than 4. And next we're going to graph this on a number line. I'll put the number line right here. I'll say 4 is about right there. All right, 4 is not included because it's strictly less than. So that means I'm going to use parentheses at 4. And notice that the less than symbol points to the left. That means everything is shaded to the left of 4, like this. Okay, and now for the interval notation. If you read this graph from left to right, this is going all the way out to -infinity. Okay, so that's what -infinity means. It goes out to the left. So from -infinity up to 4, and not including 4. That's your interval notation. And keep in mind, infinity, whether it's positive or negative, always uses parentheses. And then for the set builder notation, I just say set builder. It's going to be this. The set of all x such that x is less than 4. Okay, here's another example of a inequality. This one has fractions in it. Let's say we had this. X minus 4 divided by 2 is greater than or equal to x minus 2 divided by 3 plus 5, 6. All right, so the first thing we need to do here, and I'll rewrite that equation or inequality. All right, the first thing I need to do here is find the least common denominator of 2, 3, and 6. I need the smallest multiple that is divisible by 2 and by 3 and by 6. And in this case, it's going to be 6. Because I know 6 is divisible by 2, 6 is divisible by 3, and 6 is divisible by itself. So 6 would be your least common denominator. And then we're going to multiply each and every term in that inequality by the LCD of 6. Okay, so in this case, I'm going to have 6 times x minus 4 over 2. That's greater than or equal to 6 times x minus 2 over 3 plus 6 times 5, 6. In this case, I'm going to simplify all of this. So on the left side, this 2 goes into 6 3 times. So I'm going to have 3 times the quantity x minus 4 is greater than or equal to, this 3 goes into 6 2 times. So I'm going to have 2 times the quantity x minus 2 plus 6 times 5, 6 to 6 divide out, you're left with 5. So this is what I have. 3 times the quantity x minus 4 is greater than 2 times the quantity x minus 2 plus 5. And then next we're going to remove the parentheses and combine like terms on each side of this inequality. So on the left side, 3 times x, that's 3x minus 3 times 4, that's 12, is greater than or equal to 2 times x, or 2x, minus 2 times 2, that's 4, and bring down the plus 5. Now on the right side, you need to combine like terms here, so I'm going to bring down 3x minus 12 is greater than or equal to 2x, and then negative 4 plus 5 would be plus 1. And then next, I'm going to move the variable terms over to the left-hand side. So I'm going to move the 2x over to where the 3x is by subtracting 2x on both sides. Now 3x minus 2x will be x minus 12 is greater than or equal to 1. And then to solve for x or get x by itself, you'll add 12. That would mean x is greater than or equal to 13. All right, so now I'll graph that solution set on the number line. Say 13 is way over here. All right, greater than or equal to means that 13 is included in the solution set. So I'm gonna put a bracket at 13. And greater than points to the right. So that means we shade to the right of 13. And in case it asks for the interval notation, it'll be this. 13 is included, so we put a bracket at 13. This goes on indefinitely to the right, so we use positive infinity and a right parentheses. And then for set builder notation, we write it like this: the set about x such that x is greater than or equal to 13. Okay. All right, next we'll look at inequalities that have unusual solution sets. Because sometimes these inequalities will have solution sets where it is either going to be the set of all real numbers or there will be no solution. So if you attempt to solve an inequality that has no solution, you will eliminate the variable and obtain a false statement such as 0 is greater than 1. Or if you attempt to solve an inequality that is true for all real numbers, you will eliminate the variable and obtain a true statement such as 0 is less than 1. That does happen, as you're going to see in these two examples here. Here we're going to solve each inequality. Like 3 times the quantity x plus 3 is greater than 3x plus 2. Now on the left side, I'm going to remove the parentheses here. So if I do 3 times x, that's 3x, plus 3 times 1, that's 3. That's going to be greater than 3x plus 2. Now watch what happens when I subtract 3x on both sides in an attempt to get the variable on the left side of this inequality. Notice 3x and a minus 3x, they're gone. 3x and a minus 3x, that's gone. You're left with this. 3 is greater than 2. And is 3 greater than 2? It is. It is a true statement. It is true. So when you get a true statement like that, that means this inequality will be true for all real numbers. And in some cases, that solution set can be something like this. The set of all x such that x is a real number. Or it could be like this in interval notation, negative infinity to infinity. So if you were to graph that on a number line, you have to shade the entire number line in both directions. All right, the other one, x plus 1 is less than or equal to x minus 1. Now, in this case, if we attempt to get the x's on one side of this equation, preferably on the left side, by subtracting x on both sides, you see these x's are gone, and so are these x's, they're gone. This is what you're left with. 1 is less than or equal to negative 1. And is 1 less than or equal to negative 1? Absolutely not. That's a false statement. So in other words, your solution set has no solution, or they use the inequality symbol for a solution set. And if you were to graph that on a number line, you won't be able to do so. You just have a blank number line. Okay. All right, next we'll look at compound inequalities. Compound inequalities. A compound inequality consists of two inequalities expressed in a shorter form with the intersection being implied. So in this case, if I have negative 3 is less than 2x plus 1 and 2x plus 1 is less than or equal to 3, these two can be combined using the intersection, and it can be written like this. Negative 3 is less than 2x plus 1 and less than or equal to 3. Or more appropriately read, 2x plus 1 is greater than negative 3 and less than or equal to 3. Now, to solve a compound inequality, we always perform the same operation on all three parts of the inequality in order to isolate the variable in the middle. Okay, because you have a left side, the middle, and the right side of that inequality. You perform the same inverse operation on all three parts to get the variable by itself in the middle. Like in this example right here. Here we got 1 is less than or equal to 2x plus 3 and less than 11. Okay. So our objective here is to get this x by itself in the middle. We're adding 3. So the opposite of adding 3 will be to subtract 3. So on the left side of this inequality, I'm going to subtract 3. In the middle, I'm going to subtract 3. And on the right side, I'll subtract 3. So here I'm going to have 1 minus 3, which is negative 2, less than or equal to 2x, and less than 11 minus 3, which is 8. And now I still need to get x by itself. I'm multiplying it by 2. So what's the opposite of multiplying by 2? We have to divide by 2. So on the left side, I divide by 2. In the middle, I divide by 2. And that should not be negative 2 here. And then the right side, we divide by 2. We're dividing by positive 2, by the way, on the left, the middle, and the right side. So now negative 2 divided by 2, that's negative 1. It's less than or equal to 2x divided by 2, I'm left with x, and then less than 8 divided by 2, which is 4. So this is 1 is less than or equal to x and less than 4. Or we can say x is greater than or equal to negative 1 and less than 4. Now let's graph this inequality on a number line as indicated in the directions. Okay. Now for the negative 1, it does have less than or equal to, so we need to put a bracket at negative 1. But at 4, it's strictly less than, so we need a right parentheses at 4. And to indicate that x is in between negative 1 and 4, we'll shade in between those two. And then for my solution set in interval notation, the negative 1 has a bracket, so we'll put negative 1 there, and the 4 has a parentheses. So that's what your that's what your interval notation looks like. Now for your set builder notation, that's this a set of all x such that, and we copy that inequality statement. Negative 1 is less than or equal to x and less than 4. All right. Okay, the next thing we'll look at is absolute value inequalities and how to solve them. So we're going to be solving inequalities using with absolute value in it. Okay, here it is. If x, or capital letter X, is an algebraic expression and C is a positive number, then you can have two possibilities here. The absolute value of x If it's less than or equal to, then you're going to write it as a compound inequality, where the x, which is your algebraic expression, will be in the middle. The constant will be negative. It'll be negative with the less than symbol and less than the positive constant. So it end up being negative c is less than your algebraic expression and less than your constant. Okay. Algebraic expression goes in the middle of your two absolute values. Your c will be negative on the left, c will be positive on the right. Or this second case could happen. If you have the absolute value of x greater than c, you're going to write that as two separate inequalities. One will be x is greater than c without the absolute value. The other one will be x is less than negative c. The first inequality you'll write without the absolute value, but on the second one, you have to switch your inequality symbol and change the sign of the constant to the opposite sign, to negative. And these apply if you have less than or equal to and greater than or equal to. So let's see what I mean by this when we do a few of these examples like this one. Here we're going to solve and graph the solution set on a number line. Here got the absolute value of x minus 2 is less than or equal to 5. Or just less than 5, not less than or equal to, just less than. Let's take a look here. Our inequality symbol is by itself. We need to look at our inequality symbol to determine which one of these cases we're going to need to use here. It says less than. So we have to use this case right here for the absolute value of x being less than c. We have to write it as a compound inequality as you see here. So that means this x minus 2 inside the absolute value bars will go in the center of your two less than symbols. The 5 on the left would be negative. The 5 on the right would be positive. Okay, here I'm just following this format for the absolute value being less than a positive constant. And now we can get x by itself. We're subtracting 2. So the opposite of subtracting 2 would be to add 2. And since we're dealing with a compound inequality, I need to add 2 on the left, add 2 in the middle, and add 2 on the right. Because this is a compound inequality that I'm solving. So now negative 5 plus 2 is negative 3, less than x, and less than 5 plus 2, which is 7. Okay, so here this will be x is greater than negative 3 and less than 7. Now, if I plot this, graph this on a number line, as indicated in the directions, let's see, negative 3 is to the left, 7 is to the right. Both of these inequality symbols are less than. So at negative 3 and at 7, I need to put parentheses at negative 3 and 7. And to show that x is in between negative 3 and 7, we shade in between. Okay. And of course, the interval notation would be negative 3 up to 7. And those endpoints are not included, by the way, as you can see in the graph. And then for the set builder notation, that will be the set of all x such that negative 3 is less than x and less than 7. So I'm just copying over that solution for the inequality statement. Okay. Now, in this next example, here we got an absolute value inequality, but here we have to get the absolute value by itself before we do anything, before we determine whether or not we have a case 1 statement or a case 2 statement. Here we got -3 times the absolute value of 5x minus 2 plus 20 is greater than or equal to -19. So the first thing I'm going to do is copy this over. Should be 5x minus 2. Plus 20 is greater than or equal to -19. Now, the first thing I need to do is isolate that absolute value. That means I need to get rid of the plus 20, and I need to get rid of the -3 that's in front. I'm adding 20, so I need to subtract 20 on both sides. So I have -3 times the absolute value of 5x minus 2 is greater than or equal to -39. And now to get the absolute value of 5x minus 2 by itself, I'm multiplying by -3, so I need to divide both sides by -3. Now, what happens here is this. I'm dividing an inequality on both sides by -3. That means this greater than or equal to symbol changes to less than or equal to. And then -39 divided by -3, that's going to be 13. So I got the absolute value of 5x minus 2 is less than or equal to 13. Now I need to look at my inequality symbol and determine which one of these two steps I'm going to need to use here. Either the first or the second. Well, since I get less than or equal to, I have to use the first case. Okay, because that case also applies for less than or equal to. So I have to write this as a compound inequality in this format. And what that means here is this. The 5x minus 2 inside the absolute value bars goes in the center of your two less than or equal to symbols. The 13 will be negative on the left. The 13 will be positive on the right. So this is the compound inequality that I have here. So now I need to get rid of the -2 by adding 2 on both sides. In fact, it's a compound inequality. I need to add 2 on the left, in the middle, and on the right. So in this case here, -13 plus 2 is -11. And that's going to be less than or equal to 5x and less than or equal to 13 plus 2, which is 15. And now I still need to get x by itself. I'm multiplying it by 5, so on the left side, in the middle, and on the right side, I'll divide by 5. So I'm going to leave this as -11/5. That's going to be less than or equal to x, less than or equal to 15 divided by 5. That'd be 3. Okay. So that's the final inequality there. That's the solution set. Now I'm going to graph it on the number line. Let's see, 0 will be here, 1 and 2 and 3. Okay, -11/5 is like -2 and 1/5, which is a little bit to the left of -2. So this right here is negative 11/5 here. And it is included because of the less than or equal to symbol. So I will put a bracket there at negative 11/5. And 3 is included as well. So I'll use a right bracket there at 3. And to indicate that x is in between negative 11/5 and 3, I'll shade in between. All right, let's look at one more example of this, of solving an absolute value inequality. Let's say I want to solve and graph this on a number line. Here I got 18 is less than the absolute value of 6 minus 3x. Now, I prefer to have the absolute value on the left-hand side, okay? So I'm going to do that. I'm going to put the absolute value of 6 minus 3x on the left side. But when I do that, this inequality symbol will change from less than to greater than. So I've got the absolute value of 6 minus 3x is greater than 18. Okay? And these two are equivalent because notice this inequality symbol points at 18. And I want that inequality symbol, if I switch it around, I want that inequality symbol to continue to point at 18. So that's why I did it like this. Or think of this. It's true that 10 is less than 18. Now, if I switch the 18 and the 10 around, then I have to say, is 18 less than or greater than 10? Of course, it's greater than, because that inequality symbol needs to point to the smaller number. Okay. So I'm doing the same thing here in this problem. All right, now the inequality symbol is the absolute value symbol is by itself, but let's look at our inequality symbol. This time it's greater than. So with greater than, it's a case 2 situation. This means I need to write this as 2 separate inequalities. 2 separate inequalities. Here's the first inequality. It's going to be 6 minus 3x is greater than 18, and that's without the absolute value symbol. Or 6 minus 3x, on the second inequality, we switch from greater than to less than, and we make positive 18 become negative 18. So here you're going to solve 2 separate inequalities here. All right. So let's start with the first inequality. 6 minus 3x is greater than 18. Well, if I subtract 6 on both sides, we got negative 3x is greater than 18 minus 6 is 12. And then divide both sides by negative 3. When you're dividing both sides by a negative in an inequality, this greater than symbol changes to less than. And then 12 divided by negative 3 is negative 4. And then for the second inequality, 6 minus 3x is less than negative 18. Again, if we subtract 6 on both sides, this means we're going to have negative 3x is less than negative 18 minus 6 is negative 24. Then divide both sides by negative 3. Again, when you're dividing both sides by negative, this inequality symbol changes from less than to greater than. And then negative 24 divided by 3, negative 3 would be 8. So this is x is less than negative 4 or x is greater than 8. All right, so here's the graph on the number line for this. And I'm going to show you. This one's a little bit different. for x is less than 4. Well, the -4 is not included, so we use a right parentheses at -4. Less than means it goes to the left, so we're shading indefinitely to the left, like this. And for x is greater than 8, well, 8 is not included, so we use a right left parentheses at 8, shade to the right, because the greater than symbol points to the right, like this. So that is what your graph looks like for this particular inequality. Now I'm going to show you the interval notation for this. If you go from left to right, this will be from -infinity up to -4. And we use parentheses. Now the word or means we must use the union symbol, because that's what that means, or. And then we go from 8 all the way out to infinity. 8, we use the parentheses out to infinity, like this. That's the interval notation. And now for set builder notation, that's going to be the set of all x such that, and we just copy all of this down right here. X is less than -4, or x is greater than 8. Okay. All right, so that's how we solve absolute value inequalities here. Okay, and that will conclude this video on section 1.7, dealing with linear inequalities and absolute value inequalities. Please feel free to email me if you have any questions about the examples presented in this video or the homework in my math lab.